Good morning, everyone. Let me just make sure you can hear me well. All right. It is such a pleasure to be here with you today, to be back in the motherland speaking about something that I am very passionate about. Now, I know a physics lecture this early in the morning might seem like a bit much, but I think it will be fun. And if it's not, do not tell me that. Please lie to me. Okay, so I will be talking about quantum technologies. The session today is about emerging technologies, and there is nothing bigger, maybe except for artificial intelligence at the moment that people talk about, except for the quantum. So we'll just go to the next slide. So headlines like these have been all across my feed. Promises that quantum computers are going to change the world, promises that they're going to revolutionize all kinds of industries. Every single day there's a new discovery. In fact, even the Vatican just organized a workshop last week to spread awareness about quantum technologies, which is quite funny because it is usually not the first to speak about new emerging things. So one other thing that I thought would be a good reason to speak about this topic is the fact that a number of countries are competing at the moment as to who is going to achieve the quantum advantage first. So China has been an early investor and at the moment is investing over $15 billion in developing quantum technologies all across, in all of their research labs. On the other hand, the United States, while it lacks in public funding, has been leading in private equity and startups that are developing these technologies as well. European Union has just announced another initiative, as well have Canada, Japan, India. So all across the world, countries are investing a lot of money into developing these technologies in order to be the first to have working products. So now, why is this the case? So a recent, just a week ago, this quantum potential report came out from Canada, highlighting the importance of quantum technologies and why these countries are investing so much money in them. And one of the things is that they are believed to revolutionize many industries. But most importantly, the reason China and the United States are competing over them is this last sentence, which is that domestic industries will need to develop these technologies in order to protect their citizens, as a lot of these technologies have a potential to break current encryption and be used in many, many ways than just for positive ways. So we're going to talk about two aspects of quantum. We're going to talk about the science and the technology aspects. So as you can tell, we have some clicker issue, but we should be doing just fine. So the science is what I study. I'm a theoretical physicist, so I'm concerned with the laws that govern the physics at the quantum scale. But what we will care about here is also the technology, which is how are these physical laws being exploited to develop technologies that will help us in our daily lives. So quantum, as a word, just stands for the smallest unit of something. So discovery that energy is quantized was quite revolutionary in physics. In the 1900s, physicists proudly declared that they have figured physics out. They thought that everything was figured out more or less through electricity and magnetism and relativity, and there was not much left to discover. But the truth was that once we figured out that energy was quantized, there was actually a whole new world of phenomena to discover. So two examples of what quantum is, maybe to help you visualize, is if you think about light, light is a phenomena you see every day. A quantum of light would be called a photon. On the other hand, a quantum of electricity, as I called it here, would be an electron. Electron is also a fundamental particle, so when I talk about it as a quantum of electricity, I just mean that its charge is the smallest charge you can have in the universe. Now, there are no pictures of electrons and photons. At such small scales, we do not have an ability to visualize things very well. But I will try to visualize the concepts that I will talk about, maybe through some analogies. But quantum world is not something that we can see. I'm talking here about subatomic particles, so scales that are 10 to the negative 10 meters, so less than a nanometer in size. So quantum physics, in case I have not highlighted that yet. It's just the study of matter at the most fundamental level. So these are the things that are building blocks of everything you see around us that exist at a scale so much smaller that they have a completely different set of rules than the world that we live in. So this is what I would like to talk about, is what is this set of rules that quantum physics obeys, and why do we think that we can exploit them to build technologies that would help us at our scale. So one of the first pillars of quantum mechanics, the discovery that quite shook up the physics community, if you will, was realization that not everything in nature is a wave or a particle. Now, in our everyday life, we encounter two types of phenomena. So things can either be waves, so think about water. When you pour water into water, water does not bounce off water, they interfere. And waves in general are just objects that are spread out in space. As opposed to those, particles are well localized, like myself. They have a well-defined position, and when they interact with other particles, they bounce off or they interact in a way that causes some deformation. So these are two fundamentally different ways of existing and also interacting with the world. So with this discovery that was fundamental to quantum physics was a realization that light, for example, is both a wave and a particle. And how we figured this out was we did an experiment. So we took a very long barrier and punched two very tiny holes in it, and then we just shone some light onto that. And what we were expecting to see was that light, if it were a particle, would just go through where the barrier was open and show up on the screen as two discrete lines of light. But what happened was people observed that actually this other pattern was seen, which is much more what you would expect from a wave. If you can imagine a wave coming through a small opening, you know that on the other side, it will just sort of ripple out. And as more of those happen, they will interfere and create this inference pattern, which is not something that a particle would do. So this realization that nature has these building blocks that are both waves and particles was really odd, but it's also something that we were able to utilize to build some of the technologies, as I will mention, that are in your hands right now, actually. The other important concept in quantum physics that allowed us to build a lot of technologies initially is called quantum tunneling. So quantum tunneling is this idea that in a world that we live in, if I take a ball and I let it roll down a hill, it will pick up some energy from the fact that Earth's gravity is pulling it down, and then it can convert some of that energy into mechanical energy, which is some speed, and it can maybe climb up the hill up to a certain point. But this ball will never go over the hill, and it will also never go through the hill. That would just be really odd. I cannot go through the door. I have to either open it or go around. But in the quantum world, particles actually exist as probabilities, and they can, in fact, tunnel through barriers, as we can see on the second slide. So what ends up happening there is, even though the particle does not have enough energy to go over the barrier, it has some non-existent probability that it will tunnel through, that it will just appear on the other side, which is something very odd that would never happen at our scale, but at the scale of quantum physics, this is how things work. Now, these two concepts are actually at the foundation of many of the technologies that are currently used. So I thought we would first briefly acknowledge those technologies that we use at the moment, and then maybe talk about why is this hype around quantum technologies at the moment different, and why there's a lot more questioning as if these technologies are going to come to light. So the first generation quantum technologies that use wave-particle duality, quantum tunneling, discretization of energy, are things like MRI machines, electron spectroscopy, your semiconductors that are in your phones, in your iPhones, quantum dots that just won the Nobel Prize for Chemistry in 2023, your superconductors, which might not be as common, and things like lasers, which are really useful. I just had LASIK surgery 3 weeks ago, and thanks to this technology, I can see perfectly now. So this is what we have been able to achieve with quantum physics this far. So there's a lot of reason to believe that we can build even more technologies on the basis of other principles of quantum mechanics. So let's maybe explore those. So the other 3 principles, and I will only address 2 of them. So we will mainly talk about superposition and entanglement, are the foundation of the quantum technologies of the 2nd generation. So superposition, and these are both very odd, so I will try to make them simple, but if someone wants to talk more in depth about the nuance behind these, we can definitely do that later. So superposition is this idea that a quantum particle can exist in multiple states at the same time. So that would be as, for example, me being here giving a talk and also being in my bed, getting the sleep that I need at the same time. Now, of course, I can't do that, but quantum particles can. They can exist in a superposition of states, and this is something that we can use to our advantage in computing, for example. So a common example of superposition that people give in quantum physics is Schrödinger's cat. So if the video will play, we will see a cat being placed in a box and a radioactive material placed next to it. So what happens here is that if you let the cat sit in a box, every so often you can think about and ask the question, is the cat dead or alive? This is very similar to quantum physics in the sense that until you measure the state of the system, it exists in a superposition of all of the states, which means that until you measure and open the box, the cat is both dead and alive, and any combination of probabilities of being dead and alive, all at the same time. But once you open the box, you reveal that the cat indeed has to be in one particular state. And this fact that measurement causes these quantum particles to take on a discrete state is the reason that we exist as we are. Quantum states, they decohere as they interact with their environment, and so this is why we don't see these effects at our scale. Another way to think about this is in a classical world, if I am at a crossroads about something, I have to pick one way, and I can only go one way. I can, of course, go back and then take the other way, but there is no way that I can take both paths at the same time. Quantum particles can take both paths at the same time. And this is not just a matter of semantics, of saying, well, a cat is both dead and alive, but if you measure it, it's actually dead. We can actually use the fact that they exist in the superposition for computing. They can actually traverse and solve problems in parallel in this way, in a much more practical sense. Okay, so then we can move on to the second concept, which is the entanglement. Entanglement is probably the oddest concept in quantum physics because it is something that really troubles a lot of physicists. Something that a lot of people often take as some kind of magic or something spooky and weird is this fact that quantum particles that are entangled, no matter how far apart they are, no matter what the distance is, once you measure one and you reveal its state, the other particle that it is entangled with will reveal the same measurement, even if they're farther apart than the speed of light could traverse. So this is something called, sometimes people call this spooky action at a distance, but not spooky if we consider that, if we think about it from the perspective of information. But it is something that we use in quantum computing, as I will shortly explain, to do computations. So we can maybe go to the next slide. So we can maybe demonstrate this with coins. So we have all done some stat problem in school. You have 2 regular coins. And what we can do is we can toss a coin, it will spin in the air, and then when it falls, it will have a particular value. So you can imagine as the coin is spinning, it's in some superposition of different states, but once it lands, it has a particular value. Now, if these coins are fully independent of each other, they are not entangled, what I would expect to see and maybe you can even guess before I show you the answer, what would the probability be of it landing both tails or both heads? 1/4. There's 4 possible outcomes, 1 that you observe, 1/4. But if the coins are entangled, and I tell you that they are entangled in a way that if one shows tail, the other shows tail as well, no matter how far apart, no matter when the measurement happens, no matter no physical distance, if I toss one coin, the other one will have to land to be the same. There is no uncertainty. They are fully entangled. So this is not something that exists at our level as well, but it is a very fundamental principle that is at the foundation of a lot of the new technologies. So then adding superposition and entanglement, we come to this group of technologies that I call second-generation quantum technologies. And we have 3 main ones that I will talk about. I will not get to address all of them in detail, which is sad, but I will talk about one of them and maybe briefly mention another one, and then we can see if we have time for more. The one that I think is going to be most exciting but is least talked about is quantum sensing. So we use sensors every day for everything, from GPS to the way things are imaged in hospitals. We are always trying to measure something from your clocks onwards. And so quantum sensing is actually this idea that you can use these subatomic particles that are extremely sensitive to any change to detect the smallest movements and smallest changes in temperature, pressure, really anything you'd like to measure. This would allow you for an extremely highly precise measurement, and I will talk about applications of this shortly. The technology that is most talked about and that the hype exists around, and I will try to address if this hype is warranted, is quantum computing. This is probably the easiest one to visualize because we use computers every day. We understand that there are so many problems that if we can just have faster computers, we could solve everything from developing new drugs to solving maybe issues related to climate change, these very complex systems that we try to simulate all the time. So of course, quantum computing seems to be the natural forerunner in these technologies, and it is what the companies are investing a lot of money, from IBM to Google. There is a race to achieve both quantum supremacy, but also to prove quantum advantage, because turns out our classical computers are really, really, really good as well. And then the last one is quantum communication, and this is the one where things get a little bit tricky with issues like cryptography, quantum networks, a different way to send information that would imply that information would be much more secure than it is at the moment, because in quantum systems, as I mentioned earlier, once you observe something, you collapse its wave function, which means it can never go back to what it was. You can always detect if an intruder tries to read your system. Okay, so let's talk about quantum computing, since I see we have enough time, I'd say. So quantum computing is where all the hype is, but it is also, if you ask any of my colleagues that are actual physicists, a lot of from our point of view, a lot of the concern comes from that this hype is going to really be negative for the scientists working on the research, because expectations of this technology have just simply been set too high, as well as the expectations of how fast it might develop. So quantum computers are not just a better, bigger, faster version of classical computers. That's what supercomputers are. Quantum computers are a fundamentally different way to do computation. So in a classical computer, you do your computations with bits. What that means is that you have 2 states your system can be in, a 1 and a 0. It's like a switch. You can be on or off. Electricity can flow or not. And your transistors build logic gates based on this. They read 1 and a 0, and they add, or they do an OR. They do some logical combination of these, and this is how they read and store information. This is how they process things. So 2 to the power of however many bits you have is the power of information you can process. Now, quantum bits are different. Quantum bits are like having a classical bit they can be in a state 1 or 0, which on this sphere, I will simply have you visualize as north and south. So if you're north, you're in a state 1. If you're south, you're in a state 0. But because of the superposition, they can be in any state between as well. They can be any combination from 1 to 0 with some probability of being in some of these states. And not only can they be in any number of these states until they are measured, they can also take all of those paths as they compute at the same time. So as they compute, they have many more states that they can be in, and they can also all go at the same time. Now, this is different from parallelizing your computations, which classical computers can do, because parallelism refers to the fact that you take one long task and you have a way to break it up into independent segments, and then you do the math on each independent segment. This is different because you are doing the computation in parallel on the entire system. And these correlations due to entanglement allow you to do this. So quantum computers are exponentially more powerful in a very different way. So they're never going to be used to stream Netflix or Instagram or take pictures maybe, but they're extremely useful in simulating the nature that is quantum itself. So for example, for drug discovery, for fundamental physics research, some of the other applications I will mention as well. So quantum computing, mainly a combination of superposition and entanglement. Qubits also can be made of many things. So there are many competing technologies at the moment, because all you really need is some particle, some subatomic particle like a photon or an electron that you can manipulate in some way. So an electron, you can apply some magnetic fields maybe and change the spin, and that spin can correspond to this block sphere and the state of where your qubit is. Or for example, you can use photons like light, you can polarize in different directions as well. So you can do that as well. But oftentimes these technologies require 0 Kelvin temperatures, so they consume a lot of power and they're not easy to maintain, and I will explain the challenges behind why. But we have but we have many ways to construct qubits. Thank you. So some common misconceptions that I mentioned earlier. You know, sometimes you see these titles like, Google claims its quantum computer can do the impossible in 200 seconds. And it's just a really big statement. So of course, a lot of people are going to then think that quantum computing is not only going to replace classical computers, but it's just going to be a much faster version of them. And I already sort of addressed why this is not the case, but I will briefly mention this very last point, that quantum computers will break all encryption. It is true that one of the well-known quantum algorithms, Shor's algorithm, actually developed at Caltech, is capable of factoring large prime numbers much faster than any classical computer ever could, in a matter of seconds. And this is what a lot of encryption at the moment is being based on. But since people have realized this, they have also cleverly developed other algorithms that are not suited for quantum computers. So there are encryption methods that protect against quantum computers. So I wouldn't say this is the biggest concern for anyone, should be for anyone at the moment. There are bigger fish to fry until then. So I mentioned some potential applications. If these quantum computers were to be realized at a scale that we need, and I will mention what that scale is, they would be able to be used for drug discovery, personal medicine, chemistry, the ability to simulate such large number of molecules and fully understand and map out what happens would give us a lot of abilities. Financial modeling as well, climate. I mean, there's a reason Wall Street uses so many supercomputers. It's all they do is they do really intense modeling of very complex systems. But there's going to be some challenges with this as well. I will just briefly get to quantum sensing because I want to make sure we leave time for your questions. But the way I think about a quantum sensor is we already have a lot of great technology out there. A quantum sensor would be, say you're at a really crowded street and you're trying to listen to your music on your phone. Maybe you have some headphones, but let's say you don't have any headphones. You're trying to listen to music And you can hear the music, but you can also hear the cars honking, and you can hear the people. You can hear a lot of other things that might interfere with what you're listening to on your phone. So you might not hear every word. You might not hear all the melody. So a quantum sensor would be as if you're on the street and you put on the most advanced, most powerful noise-canceling headphones. It allows you to get the signal so much more clear. It allows for much more precise measurement of any sort. So why this is useful is, since they can detect the tiniest little changes, they can basically be used in a lot of the fields that require really precise measuring. For example, if I wanted to see if I have initial stages of some disease, the imaging that we do at the moment is okay, but imagine if you could image and see every single molecule. You could detect disease much earlier. You could also target the treatments much more precisely. Also, they're really good. Something really undervalued is atomic clocks. The fact that we can measure time extremely precisely is not a trivial task, and it is really necessary for a lot of the navigation systems, GPS. Quantum sensors would allow for much better, we probably would not need GPS as we have it today. We would have a different way to measure exactly where we are. So they have a lot of applications, and they're actually a lot closer to being a real technology than quantum computers are, for example. But I will come back to that. So quantum communication, we will not be speaking about, but this is just an effort to put quantum to everything that has to do with networks, like quantum internet, quantum cryptography, anything you can imagine that you have information science for, you put quantum in front of it, and you can kind of do the same thing. But that all follows from some of the other technologies. But the science behind this is actually what's probably the most exciting. All right, so what are some of the challenges and what is the development timeline of these technologies? Because I try to tell you a lot of the things and maybe get you excited about the potential of what the future with these technologies would look like, but how realistic any of this is. So I would say that trying to predict the future of technology is, there's a whole book on telling you that we are traditionally very bad at this. So I will not pretend that I can predict any future here, but I can tell you some of the challenges, and then maybe we can connect it to why it might take a lot longer to develop these things than it seems. So one thing that happens to these qubits, and really anything at a quantum scale, is it decoheres. For it means to decohere, it means it becomes classical. It becomes like us. So it loses its quantum properties. And it is very hard to prevent quantum states from decohering. So this is one of the first challenges. The second challenge is that we don't appreciate enough how accurate classical computers are. Classical computers do not make many mistakes when it comes to simply processing the information from ones and zeros. They're very accurate. Quantum computers, even when implemented, I think the current one that we have is about 1,100 qubits, make a lot of errors. So most of the effort in this field is going towards developing quantum correcting codes. And then the last issue that connects the first two is the issue of scalability. I would say it is remarkable that when IBM announced in 2020 that they are going to develop a quantum computer of 1,000 qubits by 2023, it is really remarkable that they did it. However, currently in 2023, we have a computer of 1,000 qubits. 1,000 qubits does not get you a lot. In order to do any of the applications I mentioned, you would need at least 4 million qubits. And this is not a small scale. This is not a small difference. It's not a small gap to bridge. It's actually quite a big gap. And things get much more complex and nuanced. The larger you get more entanglement, and these systems start to look more classical. So it's actually really difficult. This is why a lot of people are really skeptical that quantum computers are going to be available anytime soon for reasons other than scientific computation. All right, so we're at the end. So I will just briefly wrap up, maybe by summarizing some of my key points. And those are the following. Quantum physics is fascinating. The fact that we can exploit some of the properties of the quantum world is remarkable. The fact that we've been able to do it for some of our technologies already is really cool, but it is going to be really difficult to extend to some of these other things, like quantum computing. And quantum sensors, I think, is something to look forward to because they seem to be much closer to development and being commercially available even within the next 3 to 5 years for certain applications. So there's a lot of excitement and potential in these technologies, but at the moment, the hype that we're seeing is probably going to blow over, and it is going to take some time for us to actually be at the point where these quantum computers are going to impact any of our daily lives. And even then, they're always going to be used for very specific applications. So our smartphones, our laptops, they're not going anywhere. They're here to stay. So if that is the major that you selected, you're in a very good position. But if you are looking for something that is going to need a large workforce in the years to come, I would say quantum physics is one of those things. So at this point, I will just thank you for your attention. And I will ask if you have any questions.
Quantum computing experts are few and far between, so I think you should use your time and opportunity to ask any questions you might have. Sara.
Thank you, Sara. This was a wonderful...
Yes. Oh, we have a question.
Presentation. Sorry, Andre, it's...
Yes.
Here.
Oh, sorry.
Let me get up. Thank you. This is a very difficult topic to cover in a very short time, so I think you did a great job. Thank you on touching a very interesting concepts. And my question for you would be, what is the application of quantum sensing? Because I think that's something that you might be more passionate about, that excites you the most. What would be something that you would like to maybe work on?
Mainly in imaging and detecting disease early. I think a lot of disease gets detected maybe late. And even in things like treating cancer, if we can be much more precise, that would be great. We already have very good technology in some way, but you can always do better. I think it's very sad that we still have, a lot of diseases that people die from that could potentially be preventable at some point. So I think saving human life is probably the top of the list no matter what. But there are many other really interesting ways, like doing away with GPS and having significantly more accurate positioning, and that would help a lot of other systems that we have in place.
Thank you so much for the presentation. My question will be, since you made it very simple for us to understand everything, and it's quite hard for me to imagine some things you were talking about, like the thing can exist and it doesn't exist, it is and it isn't at the same time until you measure it. So I would like you to give us some resources. What can we read? What can we look into to have more information and to help ourselves figure these things out?
Yeah, I can definitely provide some resources. This becomes much easier to understand when you add math. Quantum physics is a linear theory because of the superposition. So once you write it out, things become much easier to see. This is why we don't have good intuition, because we can imagine many of these things, but we can calculate it really well. We understand the physics pretty well. So Feynman's lectures on physics are always a really good way to start. Richard Feynman is actually who started the field of quantum computing, and he was a Caltech for a very long time. Every Caltech speaker has to bring him up at least once. I think it's the rule.
Thank you so much for your amazing presentation. It was so great. I have a question. How can this be applied to telecommunications and mobile technologies?
So I'm not an expert in that particular field, but one thing is quantum internet is, well, with the whole thing with entanglement, these things are both more secure and also normally you need information to travel, but things that are entangled sort of can transmit information without really traveling. So people have already have achieved some results with this where things are just safer, faster, better in that sense.
All right, thank you so much.
Thank you for a wonderful summary of everything. I think this is one of the best presentations I've ever heard about quantum technology. But I would want to touch upon one thing that you actually mentioned, and it's quantum tunneling. I would like to ask you about quantum tunneling specifically in radioactive decays, alpha decaying, and actually discovery of new elements. Is there a possibility of actually using, for example, PET microscopes for discovering new elements and using this quantum technology, especially for that?
New elements on planet Earth?
Yeah.
I'm not sure. I think for that, a lot of the new elements that can decay in that way have to have come from some element with a higher number, and I think because of the way things decay, we're kind of at a limit unless we bring something from other planets, which gets into a whole different topic. I mean, the most you can do with decay like that is you would just change the number of electrons in the outer shell, or maybe with an alpha decay number of protons inside, but we know all the combinations, I think, from the numbers that are currently known in the periodic table. So I think that's a really good, interesting idea, but I'm not sure if that helps answer. Maybe we can talk about it more.
Okay. Thank you very much.
Of course.
Hi. A question about quantum entanglement and spooky action at a distance. How is it possible that information can be transferred faster than light?
It is a great question. The thing is that if you think about it in terms of information, it is not really being transferred. It is almost like already having been there. Information, when you transfer information, it means you're sending something new to another system. But these entangled particles, they sort of have it, they're born the same. So the way we think about them is not as two different particles. We think they're, for all sense and purposes, they're the same system, just separated really far out. So we actually don't make distinction between them. They are the same thing. When you measure one, you're really measuring the other.
And what are the implications of that technology in our society in the future?
Yes, so quantum entanglement is at the basis of a lot of the quantum computing, quantum communication. One of the implications is, for example, for quantum cryptography, the reason we think the information is safe is because if you send an entangled particle with another one and it gets interfered or measured, you who are sitting at home now know, because your particle changed state, that someone tried to observe the information you sent. The other way that particles entangled are important is in quantum sensing. So a lot of times, imaging a cell, for example, will cause it to be disrupted in decay, but you can entangle it to another thing and then measure it, and you will get the same information about the original system, but you didn't have to destroy it in that way. But this is very, I would say that people that claim to use quantum physics in biology at the moment, I would personally not be caught citing their papers. So I would allow that to develop a little bit more. But thank you for your excellent questions.
We have some questions in the back. Okay, sorry.
Hi. I just want to say, it's super amazing how excited you are about your work. But maybe I missed it. Can you just tell us what your PhD topic is in a language that we can understand?
Of course.
Thank you.
So these quantum technologies might not be that useful to commercial users, but they do allow us to study quantum physics. So one of these quantum simulators, which is just a sequence of atoms that are isolated and can be observed in their behavior, revealed a unique phenomena in quantum physics called quantum scarring. So a quantum scar would be like a quantum system having information about its initial state when it shouldn't. So the reason that classical world exists is because quantum systems, they decohere, they become classical. These quantum behaviors average out through laws of statistical physics, and so we don't see them. So for a quantum system to remember its initial state is really unique and could be really helpful in quantum computing. And we did not even know that this could be a phenomenon in quantum many-body physics until it was accidentally noticed in an experiment in 2017. So what I study is why these quantum scars exist, how do we understand them, how can we use them for technologies maybe, but more fundamentally, I'm really interested in how the classical world that we live in emerges from the quantum world, and if it's actually that direction, or if there's some direction where classical informs the quantum. This is somewhat of a debated issue.
Thank you for your amazing presentation about one of the most beautiful fields of physics. And I would like to ask you something about particle and wave theory. There was once an experiment conducted where a group of scientists got a source with constant electron flows. And they put an obstacle with 2 holes in the electron path. And they wanted to see how would the electrons behave. And they put some sensors and observers. And while the sensors were there, the electrons behaved like particles, and the image contained only 2 stripes. And when they removed those sensors, the electrons became behaving like waves, and they became interfering with each other. So why do some particles behave like particles while being observed, and they behave like waves while not being observed?
That's a great question, and a very subtle point to that as well. None of these particles are either waves or particles, really. That is why they exhibit both behaviors, but we understand it from the quantum field theory in a somewhat of a different way. So they're really neither or, but it is the act of measurement that causes them to act a particular way. And this is, so I took this quote away, but Richard Feynman said this is the only mystery in quantum physics, is the fact that this is true. You could just never imagine this to be true, but it's how nature works, or at least it seems to us today that this is how nature works. So if I had the answer to that, I would be standing on a much bigger stage.
Hello. Just wanted to ask you, I'm curious about how you keep the quantum computers cool down, because you said that it needs to be the temperatures near absolute zero. So how do you keep them cool down while they are working?
Yeah, this is an engineering question, so I don't build them, but all I know is that there are ways. So this is possible to do. We have known for a long time how to cool things down really cold, but they do use a lot of power to do this. This does not seem to be the biggest challenge from what I understand from this field, but I do not have the specific answer to that.
Okay, I must say what a wonderful presentation this was, and I'm very grateful to be here. My question is, you said this year we reached about those like 1,000 qubits. One day we will reach 4 million qubits or even more. Like, where is the limit to that? Like, are we gonna be at that point and gonna say like those old physicians, oh, we have solved physics? Like, how much you think there is more to research to
Oh, what
this?
a great question. I love this question. So I think we will always have more to understand. There are other scales that we don't understand. There's so much to explore. But this is a good point. At what point will you have enough qubits to say, I simulated the universe? I don't think that we will easily get to that point. I think it will be a lot more than just that. There's a lot of nuance. Even quantum theory that we have known for 100 years now and we find to be an extremely precise theory has its issues, and not everyone is convinced that we got it right, even with this one. So I think it is really exciting in my mind how quantum computers will be used to study nature. more than the commercial applications maybe, but we need to get funding from somewhere. So that is a really good question to ponder about. I'm not sure. Physics does not place a limit on how many qubits you can have. This is more of an engineering issue. We understand what physics says. Physics says they can build it. And I feel like if physics says they can build it, the engineers will figure out how. So once they do, we will definitely have that answer.
Hello. My question is about superpositioning. Like you said, particles are superpositioned. They're in every place until we observe them. How do they know that they're being observed? How do they know when to lock into that place?
Another great question. It is a mystery, and this is why we need more people studying quantum physics. The act, I will explain it this way. The act of measurement is not just you standing and looking at it with your two eyes. That is not what observing means. Observing means measuring, and anytime you measure it, you disturb the system slightly, and the moment you disturb it slightly, this is how they know, because they are disturbed. So it's not just, I know the experiment with the cat might make it seem like I look at the cat, but at this very tiny scale, you really disturb it, and any disturbance can cause it to decohere, lose information, or simply collapse into a particular state. But this question of collapsing the wave function is what people talk about. This observation is actually highly debated as well. There are a few competing theories, but it is again not fully answered. And this is what I think is so exciting, and I hate that more people study quantum physics. There is so much that we know, and then there's so much that we do not know. We know it works, we know how it works, we observe it, but we just do not have that fundamental understanding of like, why can it be this weird? Why can it be this way? Out of